Hello and welcome to another special episode of Q&A coming from TechCon in Houston. Today we have the special honor of having John Martinis, Nobel Prize winner from 2025, joining us here. John, welcome to the show. It is great to have you here. Maybe start with a little bit back. How'd you get here for the audience?
Well, I took an airplane here, but
that's a good start.
That's a start. I worked on an experiment, or my PhD thesis, looking for something called macroscopic quantum tunneling. And we did I would say a foundational experiment on there. And that's what 40 years later, the Nobel Prize was awarded to us for. And it turns out that experiment was a prehistoric qubit. The idea of qubits kind of hadn't been invented at the time, but we were able to show for the first time the quantum behavior of this, see energy levels, and that kind of laid the foundation for now a huge field to build these superconducting quantum bits.
So back in '85, you were ahead of your time.
Yes, but it was just an interesting science experiment to do at the time. Basically, we all know quantum is the physics of the small, of atoms, electrons, and we wanted to show that quantum could be applied to electrical devices. A chip that is about a centimeter across that you could see with your eyes. And we showed that quantum is much more applicable to many more systems, thus enabling us to develop and build these very complex systems.
Yeah, I used to always tell people that, I didn't think I'd see self-driving cars before I retired or died, So at this phase of the adventure, this quantum adventure, you've been, Nobel Prize 2025, and you started the adventure when?
Oh, for my graduate thesis, and the paper was published in 1985. So it's been 40 years. In fact, the Nobel Prize was announced 40 years to the day of the publishing of the paper we did at Berkeley.
Okay, so you lived to see your Nobel Prize.
Right.
That there's a milestone by
40
itself.
years.
40 years. And what's the milestone now? So quantum computing, fusion networking, 40 years. We're up to how many qubits? 50 to 100 of these things?
Hundreds to maybe 200 qubits. It depends how you want to quantify all of it, but that kind of measure, yeah.
And for the average layman, you say, I'm an amateur physicist, I think qubit, I think entanglement. Do I have to entangle all these things or just a couple of them at one time?
You have to do all of them at the same time, but generally you just do them in pairs.
Okay.
But then you do that sequentially so that you can entangle and make a complex algorithm. But this is how you think about bits too. You operate on, let's say 2 bits or several bits, and then you operate over and over again to build a complicated algorithm. So it's very similar to classical computation that way.
So I've looked at a lot of these little quantum startups. Everyone is in Google. We're all in the range of hundreds of qubits yet, or where are we at in the adventure?
It depends on the technology and the company, but I would say that the biggest systems now that are 100 qubits, and then of course is what's interesting people can understand. But for qubits, you have to make them well. They are naturally have some errors, so there's a lot of discussion about how you make your qubits operate properly with low errors. And there's other metrics, how fast they are. Some qubits are much faster than other qubits, and of course we all know that a fast computer is better. So there's some subtlety into how you want to think about the field.
And in my understanding, these qubits come in all different types of flavors.
Right.
Now, do they all have to be chilled down to absolute zero, or there's any qubits running at room temperature nowadays?
No, there are, let's say, atomic systems and atom systems that are at room temperature. They typically have to have very amazing vacuum. They have to use lasers to control them, which are very complicated. What I would say is every qubit requires one or more exotic, difficult technology, which over the years people have been able to perfect and get it to work well. So every qubit has its peculiarities and its difficulties. And it's kind of hard to say that one is better than the other because of those particular difficulties. In the end, it's the performance of the computer that matters.
Okay, so I always like to find the right analogy. So I make a
Yeah.
barrel of wine.
Okay.
Winemakers. I have my own preference. Your favorite qubit recipe, or which qubit are you betting on?
So if you ask any scientist in the field, they say their qubit is the best, and they'll tell you a lot of reasons for that. And what I would say in general is that usually people talk about what's good about their qubits, but in reality, if you're building a complex system and you think about system engineering, it's usually the worst characteristic that matters, okay? Whether they're slow, whether you need low temperature, whether you need high vacuum, whether you need lasers, whatever. It's very subtle. So this is what's hard for the layman to understand, is that this all kind of talked about in what's best about the qubits. And in the end, you have to really talk about what's worst and what you have to fix. People generally don't want to talk about that.
Okay.
So for superconducting qubits, we're fast. You build it like an integrated circuit. Yeah, low temperatures you can deal with. But I would say, in my view, it's the manufacturing of the integrated circuits that we have to get better at. And that's, of course, what our company is all about.
Okay.
So I explicitly talk about what's wrong with my qubits and how we're going to fix it. That's very unusual.
Okay, so you're down to like more practical. How do I get this qubit into manufacturing? Because I think you're the CTO of Colab.
Right.
Your real focus is how do we get to a practical manufacturable qubit? And I assume we're talking about trying to get this on a chip. Yeah.
But that's right.
Am I going to get 1 million qubits on a single chip, or am I going to have an array of these chips?
The qubits that we make are big, and that's actually useful because you have room to bring in wires to control them. So what we're thinking about is doing wafer scale integration and putting 20,000 superconducting qubits on a die about that size, and then we stack them together to build bigger systems. Okay. And right now they're putting 100 or 200 on one die. We want to do 20,000 and make it much more reliable than what people are doing now.
Okay, so we got 20,000 qubits on a little die, and we got to get up to a million to make this useful. I have to divide that quickly. Okay, so
around 1 million. Yeah,
okay, so we got to get a bunch. Okay, this is like early computers, like your 60s, 70s, a lot of chips to get this thing to work.
Right.
And what do you think? What's your lunch bet on, before you, what your next fate and the next milestone before you, next in your life? How many qubits are you betting to see? We have a little lunch bet on number of qubits.
So what we're working on, like this week, right away, is how to make qubits with a more manufacturable way that's really semiconductor technology kind of compatible, and to make that with a really good coherence time, to make it reliably so they have very, very high yield, and some details having to do with the two-level state physics. We want to make that better. So we have specific reliability performance metrics that we want to beat. That's what we're working on right now. And then over the next few years, we're going to work on scaling up the qubits. So right now, people talk about having to put all these wires to low temperature to control the qubits. We want to put those wires on a silicon wafer. And that way we can integrate this with one wafer, which can be run through a process, a semiconductor process very efficiently, and then being able to assemble our qubits in a very efficient way. But we're trying to bring the reliability up, the cost down, exactly what's happened with the semiconductor industry as they made CMOS chips. If you look at what's going on with AI chips right now, very powerful, very big, billions of transistors, and manufacturable. It's hard, but they'll get better at it.
Okay. So I know you're part of the Google's Prissy project.
I was, yeah.
And now in your lifetime, are we going to see a quantum computer that actually does something useful? I mean, everyone's worried about quantum computers breaking my security, my password, and the Shor algorithm, everything. Is that going to happen in our lifetime?
So what I say publicly is in 5 or 10 years, there might be a quantum computer out there, Google, IBM, someone, maybe a neutral atom company, that maybe can break current encryption, 5 to 10 years. Now, Sundar Pichai, the CEO of Google, says 3 to 5 years, but he's a CEO. He has to be sooner rather than later. He has to err in that. So I consider that. And if I look what's going on in the field, there's a lot of proposals out there where, it might be possible to do that. Now, we kind of consider that, and what we're trying to do is build a fabrication technology to help accelerate that, to make it easier. Whether we build a quantum computer or we use our process and other people build their own chips that way, we'll see. We're open to helping the community in any way we can.
But it takes around 1 million qubits to get to the short algorithm.
The numbers maybe are down to 50,000 to a few 100,000 now. They've figured out some more clever ways to do it, but the numbers have come down. But it's still significantly above what people do now. And again, you have to make the qubits good. You have to make it fast. There's a lot of things you have to do.
That seems doable. We're talking about 5 chips now. You get a couple of these 20,000 qubit chips. You're in the ballpark now.
Yeah, well, that's what we're trying to do, and certainly there have been lots of progress in the field. So there's a lot of excitement to do it. Well, one thing I would say is, even though I'll make those predictions and other people are saying the same thing, I'm going to say I think it's going to be a little bit harder than people think to put this together. Things will go wrong that you have to fix. So if it takes longer, it takes longer. There's still a lot of technology development. But mostly what I say is the people in the security environment thinking about, RSA encryption and cryptocurrency and the like, they have to be ready for that kind of time scale. And that's the biggest message I give is, this is getting serious. And, when I see what's out there and what people are proposing, this to me is a reasonable time scale to start planning for, which means you have to start working on it now.
Now, I think we know NIST has all the new PQC standards in place. Do you think those are good enough to basically thwart all the new quantum computing, or do you think those standards need to be robust?
I think the standards, there's proposals, the standards are good enough that people can think about, switching over to it. And I know Google is making a commitment to do that in 2029. And in fact, my son is a small part of the Google infrastructure helping to do that. So I'm very happy that he's doing that. People are working on it. But fortunately, people have known about this for a couple decades and have been working on it. And I would say, I don't know enough about how to do the crypto systems. But, what happens is you kind of have to redesign the whole the crypto system kind of from scratch to, and do this. It's actually a lot of work.
Yeah.
And my hope is now that people have to look at it again anew and recode this, if we come up with a better crypto system that's quantum safe, then it'll be relatively easy to put it into the newly developed ones that people do. So I think that's part of it is RSA has been around a long time and they built around it in a certain way. They have to make it more general infrastructure now. Then if we have to change, it'll be easier to change.
Yeah, I've talked to a lot of people in this quantum security concern. It seems like there's 2 components. There's kind of the key exchange component, make sure these keys are robust enough. There's also kind of this more entangled, hey, we're going to put entangled photons on my fiber to try to look for middle of the man.
Right.
Which one are you more concerned about, the keys or the middle of the man attacks?
So I'm thinking that, and my understanding is that these quantum safe algorithms is kind of like what we're doing now with classical information exchange. And then you just do that in a way that a quantum computer can't break it. And that's the generic thing that everyone wants to use, because we want to keep the basic infrastructure. I want to do, banking from my phone, and people are doing that. And then the entangled photon is maybe for ultra secure applications, let's say bank to bank transfer or something like that. That's very important too. But you really need security using the present kind of infrastructure, classical communication structure that we have.
Okay, so the other interesting discussion, this show is typically about how different spaces, verticals are using AI. I know in the fusion, they're looking to see if they can use AI to control the plasma going around the reactors and everything. So in my quantum computing, are we leveraging AI to help make these coding or error correcting the qubits? Or is AI more off to the side?
So AI, I think, is going to play a very important role, for example, in doing the error correction algorithm. So you run the quantum computer, there are errors, you have to get that data and then figure out where was the error. And there are classical algorithms right now, but I think they're going to be a little bit too slow or very hard to program, put into hardware, whereas the AI can be more generalized, more parallel process. So there's a big expectation that you'll be able to do that. I think people are still working on it, trying to prove that it works. But my guess is that'll work, and that's a very big application. Now, I'm way down at the hardware end, and we use AI for when we have materials issues, materials questions. It's a way to search the literature, and in a couple minutes, I can get a bunch of papers and a bunch of summary to kind of explain what physics is going on. So we use that all the time. We also use it, we record all of our group meetings so that if we want to, we decided something 6 months ago, we can query the AI to kind of refresh our memory what we were thinking. And that's super useful, kind of as a documenting of what we're doing.
Yeah, well, and that's always been a key part of the science community, right? Is trying to make sure you're aware of what everyone else is. So AI is trying to make a smaller world, bring everyone closer together and make it easier to find out what other people are doing in this space.
And it might be able to put couple ideas together we've had in our group meetings and help us understand that. So I think as a company, that I hope gives us a lot of value because we're capturing all the ideas we're having. Of course, not all the ideas are going to be good ideas, right? You have to filter that. Now, I'm going to say coming up with new ideas, something that's never been done before, that's harder for AI to do. That's not its strong part. So that, physicists are still needed, okay?
So you don't feel threatened yet?
Yeah, I don't feel threatened. I feel like it's helping us. And in coming up with new ideas, then, we're going to have to generate that ourselves. But AI is a really useful tool for us in this way. And, we're using that, of course.
So your recommendations in the new generation, I always hear, plumbing, dentists, physicists, these professions are all safe for a while now?
Oh, I don't know. I've heard from my professor colleagues that in the software realm, it's very hard for young people to get, entry-level coding jobs because AI has kind of taken over that. And so they really, have to start doing other things now. And I always thought that, the coding jobs were, good jobs for people who like it. And that seems to be much more difficult. Now, of course, for architecture, design, other things, then, computer scientists are needed for. But it's kind of, computer science is one of the first big issues, that's coming up for professionals.
Yeah, no, it's funny because I always tell people, it is changing. I wouldn't say, computer scientists still have a role, but in this new agentic world, it's almost like if you're an English major, it's all about prompt engineering and English.
Yeah, exactly. Yes, that's right.
Very good skills.
A different skill set than just pure coding.
It's still programming. It's just programming in a new and different way.
It's a higher level way. And now, fortunately, I'm a hardware person, and I would probably guess that AI has a harder understanding because it's more of a abstraction kind of thing, and maybe not understanding like the physical world. But we'll see what happens.
I think you're with the plumbing and the dentist.
We'll see what happens. So I'm a little bit worried about that because I'm very much of a hardware guy. But like I say, for inventing new things, we'll have to see if that'll happen. It's an interesting new world.
Okay, now, so I'm in the self-driving networking space.
Yeah, okay, yes.
Networking, quantum, two ships in the night, or somewhere the network hooks up to this quantum computing. We're building all these AI clusters. there's a lot of talk how we're going to network AI clusters and GPUs together. Same discussion in quantum or slightly different discussion? Or out of your wheelhouse?
It's a little bit out of my wheelhouse. I'm going to say my personal view is we have to, computers were invented before networking was invented. And if you want to network a quantum computers, you have to build the quantum computer in the first place. But, people are working at networking, and I'm sure that'll come into its own once we do that. But yeah, we're just trying to get the quantum computer to work properly. The other thing is quantum computer is not necessarily best structured for huge data sets, which is what networking and AI is kind of dependent on. So the applications might be a little bit different there. We'll have to see. It's hard. And then, first of all, algorithms and thinking about that is not necessarily my forte. I'm really thinking about building the hardware.
Now I know you're working with HPE. What's the relationship between Colab and HPE?
So building a quantum computer takes a lot of different skills, and we're focusing kind of at the low hardware end. We work with other companies like at the intermediate control end, and we're specifically working for HP Enterprise because of their knowledge about supercomputers. Because obviously, if you have a quantum supercomputer, you're going to be co-processing with a regular supercomputer.
So this is like the accelerator on the side. Hey,
you think of it as an accelerator. So it's very natural to work with HPE in that way. Now, one of the things that HPE is knowledgeable about, and as well as some other companies, is kind of the algorithm space and how you're going to run algorithms and the like. And that's very important to talk to people all the time. We just had a conversation with someone at lunch over this, to know kind of what's the overall high-end architecture so we build the hardware in the right way. So, I try to keep up to that too, as much as I can.
Okay, now, we look like we're kind of the same age group here,
Right.
We've seen the little things over our career. It's hard to believe we started with no computers and everything. When we look at AI, quantum computing, just another technology that we have to adapt, or is this more of the industrial revolution type of thing? Are we impacting society, or is it, are we going to replace, create more jobs than we replace? That's kind of the typical new technology.
So obviously I'm quite interested in quantum computing because I think it could be extremely impactful. And we all know that computing is important for everyone's lives. And if we can build a computer that's way more powerful in a specialized way, in a co-processor way, this can make a huge difference. And that's why I think it's just important to work on the technology because of the promise. But I think it's gone far enough in my career to see that it's likely this will get built. And then we have to see in the end how clever we can figure out to use it. But I think it can make a very big impact.
Okay, so now if we take Shor's algorithm, the whole security, biggest impact on the average everyday human, chemistry, new drugs, quantum computing is going to open up something.
Yeah, so, in terms of Shor algorithms, I would hate for my legacy to be breaking the internet or breaking Bitcoin. And I think there are protections against that. People will figure it out and it'll be okay. It'd certainly be interesting when people demonstrate that. But, for me, especially as a physicist, I think a lot about the applications of quantum chemistry or quantum materials. We're all used to using a classical computer to design our electronics. We designed our kitchen on that, mocked it up. If you can design drug interactions or chemistry or how to build better transistors with a quantum computer, that can make a huge impact in the way regular computers are. So I'm more thinking about that. And whether this will impact the average person's life, well, computers do. People want to electrify transportation, and if you can find better materials and use not so rare earths to make motors instead of rare earths, that can have a very big impact on society. So, we all know that computers are important and powerful, and that's kind of where I'm thinking I would like that to be my legacy, put it that way.
So maybe any final words of wisdom for the audience here?
Just keep an eye on quantum computing. There's a lot of things happening. It may take only a few years, it may take longer, but it's just, I think it's really coming at this point. There's a lot of good ideas there, and we just have to give it time to mature. Just like in AI, people that were working on these kind of AI models for a long time, and then there was just an explosion in the last few years as they got very powerful and they scaled it up.
I'm with
we
you.
have to do the same thing.
I'm hoping before I retire, I see self-driving networks come in. But John, I want to thank you. This has been for me personally, I'm an amateur physicist, so it's been a true honor to have you here.
Great.
Thank you for joining us.
Yeah, it's been my pleasure. Thank you very much.